very happy today. We have a guest speaker, Yun-Fei Liu.
Yeah. Good.
All right, so he's going to talk about human mind behind the machine. Sounds very interesting.
Yeah.
All right, so the floor is yours.
Cool. Thank you. So good. Still morning, right? So good morning, everyone. And yeah, thank you for your kind introduction and the invitation. So it's my great pleasure to share with you my work and my prospect. So I am a cognitive neuroscientist from Johns Hopkins University. The fun fact is that there is a cognitive science department and a neuroscience department in Hopkins, but I'm in neither of them. For some historical reasons, our department is called Psychological and Brain Sciences. That's where I work as a postdoc in the lab of neuroplasticity and development, led by Dr. Marina Bentley. And before that, I had an undergraduate training and degree in electrical engineering. And this background kind of inspired my interest in how our minds and brains interact with technology and how the brains are shaped by this kind of interaction. My research program is largely driven by two overarching questions. First of all, how does our evolutionarily ancient brain enable us to use modern technology? And second, what neuroplastic changes take place when we learn the new technological skill? So it's a miracle that we can use any of the modern technology we are enjoying right now, especially when we consider the evolution. So just think about this. We're using this almost the same brain as our Homo sapiens ancestors to do something that they never even had a chance to imagine. And this is amazing. In terms of evolution, we humans possess some very ancient cognitive abilities like object recognition, number approximation, and language. And our brains already come up with some specific mechanisms for these guys. On the other end of the time scale, we have the skill to use modern technologies or cultural inventions. So the skills like driving, gaming, playing musical instruments, weaving, and even doing scientific research. These things are so new that our brains just couldn't have enough time to come up with some genuine solutions for these guys. But the amazing thing is that even though our brains are did not evolve for these tasks, any healthy human being can learn to do these things. And many of us are even masters of these skills. So my research addressed how we do this, address this amazement. And I'm particularly interested in what I would call cognitive technology that includes things like reading, writing, or math, and programming. So these are the symbolic systems that expand our thought, allow us to convey our knowledge, and also communicate with each other and the machine. So I have done a project on natural reading with sighted people and braille reading with congenitally blind people. And I've also done another project on shared experience. So that's how our neural response is synchronized across people listening to the same story. Today, I'm going to tell you about my work on programming. As you can tell, this has become my primary research program with these publications. Programming is my test case for how human minds and brain acquire a cultural skill. But why programming? What makes it so special? Well, just think about what underlies our modern alphabet from AA, Amazon to ZZ, Zoom. Okay. I know some people argue that ChatGPT is going downhill and it should be replaced with Claude. Okay, yeah, sure, CC Claude. No problem. Be my guest. And yeah, then you're okay with WW World of Warcraft. So this thing has been in my life for from 2004. So let me show a little bit of appreciation. Okay, I know a lot of talents have been poured into these products and services, but their backbone is programming. Yes, and see, what programming has brought us recently? The AI, coding copilot, yeah. So Atlas Institute is a place where people make things, so I believe that includes a lot of programming. So has any of, maybe I should, no, not any of you, has any of you not tried yet programming with some kind of AI help? Well, I can't tell you, yeah. No, you don't have to admit right now. So yeah, these guys are very capable. Especially for local edits like this one. Of course, they cannot manage like projects of thousands of different scripts, but for local edits like this, it's pretty capable. I can just type what I want as a comment, and then it just come up with this completed function. And that's cool. And I would say it's also not redefining, it's expanding the definition of programming. It put forth this ability of computational thinking to like algorithmically lay out the steps we are going to do to solve a problem. Of course, software engineers have been doing this all along, but the popularity of AI is bringing this skill into public awareness with all those prompt engineering, celebrity courses out there. Yeah, maybe not the best example, but people are getting more aware that computational thinking is an important skill. So the idea of programming is evolving from punch card to assembly language to higher level programming languages to today we have algorithmic and thoughtful and plus careful debugging to avoid disasters, of course. And I would say this isn't even its final form. Okay, so what will programming be like in the future and how do we learn them? So the cognitive neuroscience of programming can help answering this question. So just like if we know human anatomy, that would inspire ergonomic product design. If we know human physiology, that would encourage human-centered work environment and schedule. I hope that's true. And if we know how the brain learn to program, it can enable us to design education programs that more efficiently teach programming its current state, or maybe reinvent programming tools, or even human-computer interface to make it more optimized for the brain to learn. And these will begin with this more specific version of my overarching questions. First of all, how does our ancient brain enable programming, and what neuroplastic changes happen when we learn to program? So in the remainder of my talk, I will tell you about the attempts I've been doing and what I found regarding the first question. And the second question, that would be a question for future directions. Okay, so this first question, it has these 4 specific components to it. How does the brain learn to program? What's the trajectory of this learning? The precursor of programming ability, and what's the behavioral predictor of the learning outcome? So each of these questions will become more specific when we come to that point. So the first question, how does the brain learn to program or to do any cultural skill at all? This is a big question in cognitive neuroscience, and there has been 2 major hypotheses. So first of all, maybe the brain learns through a general purpose learning mechanism. So in this view, the brain is a collection of interconnected nodes, and learning happens as the adjustment of weights between these nodes. If this sounds familiar to you, because this is the view that inspires artificial neural network, which empowers the large language model and of course AI. And the support for this kind of view is the fact that programming ability does emerge in large language models like these guys. And we know these AI models, even with all those billions of parameters, they are still way, way simpler than our real brain. So if these models can learn programming through a general purpose learning mechanism, it's reasonable to assume that our brain can also do this kind of thing. The alternative hypothesis is called cultural neural recycling. So it stems from the idea that the brain does not start as a totally blank slate. Our brain evolved for specific tasks like object recognition and number approximation. And if, when we learn some new skills, when the new task demand is at least superficially similar to some ancient task, that neural mechanism for the ancient task gets recycled or augmented to support the new task. So one example of this cultural recycling is reading. So when we read, there is a specific region in our brain that gets super excited by the presence of visual words. And this region is called visual word form area. It's at the left bottom half of our brain, close to the back. And in the brain of an illiterate individual, this region does not respond to words, and instead is activated during object recognition. It's only after we are trained how to read does this region show selective response to written words. Otherwise, it's just for object recognition. So this is the reason why people say that object recognition is recycled for reading. All right, so back to programming. If programming is like reading, which is recycled from some ancient cognitive abilities, then what is recycled? A prime candidate here is language. Perhaps programming languages are called languages for some good reasons. So first of all, both natural language and programming language are governed by some kind of grammar or syntax. A short sentence like the dog likes ice cream can be decomposed into a syntactic tree like this. So it's true for any code snippet, like if A equals 3, add 5 to A. Well, no matter why we're doing this, this is the syntactic tree of this snippet. And what's more, there's this view that there are no unambiguous demonstrations of recursion in other human cognitive domains, with the only clear exceptions, parentheses, mathematical formulas, computer programming, parentheses, being clearly dependent upon language. So in linguistics, recursion means to embed a phrase or clause inside another phrase or clause of the same type. An example would be a sentence like this with a nested noun phrase regarding a cat, a mouse, and a piece of cheese. So we have this kind of recursion in program, definitely. Theoretically, we can have as many nested layers of for loops as possible. Although I know in practice, I think the suggestion is like no more than 5 layers or 3. Yeah, but that's recursion in programming. And we even have the formal definition of recursion, which is having a function call itself inside its own function definition, like this example of computing a factorial. So these are reasons why people think language network might be recycled for programming. And another candidate would be logical reasoning, because even without the need for programming, we do this kind of algorithmic and mental gymnastics every day, like some classical syllogism. All humans are mortal, and this guy is human, therefore he is mortal. And something else, maybe like the modus tollens reasoning. So if someone gets an offer, he will definitely come work here. And so if you don't see him work here, it means whatever. Okay, so, and you might occur to you that logical connectives like these guys are everywhere in programming. That makes the demand for logical reasoning pretty explicit. There's this view, this hypothesis that logical reasoning is conducted through a language of thought. This language of thought is different from the natural language we speak, and it engages a different system than the language network in the brain. Even though reasoning sometimes begins with linguistic input, it's not carried out by the language network. This independence of reasoning from language might be more apparent when we consider some nonverbal tasks like this, where you identify the regularity among the patterns to select the missing tile, or this nonverbal disjunctive reasoning task that people present to babies for them to like disambiguate the two objects to derive this object could have been either of them. And if you see that this object is not in the ball, you know that in this ball is the other object. So this kind of nonverbal reasoning task presented to the infant. Now this is a paper presented on science. That's amazing. Like by doing this, you can have things on science. That's good. And also like no, I'm not despising it. I mean, it's good. It means cognitive science has its value. Yeah. And also some tasks like predicting the next item in a temporal sequence. So in these things, perhaps programming involves much of solving logical puzzles like these rather than generating natural discourse. And in some of these reasoning studies, they explicitly call this kind of pattern finding ability mental programming. So maybe this kind of highlights why people think reasoning network is recycled for programming. Okay, so these are our hypotheses, and I'm testing them using neuroimaging methods. So if the brain learns how to program using a general purpose learning mechanism, perhaps we could expect everyone to have a different response to programming code, because it's just like when each time we train the model from scratch, we will get a different set of parameters. And if the brain learns to program through cultural neural recycling, the neural response to programming should overlap with our candidates, language or logic. But how do language and logic look like in the brain? Fortunately, there are some validated tasks to localize the language and logic network inside the brains of individual participants. So in other studies, not mine, language network usually look like this, particularly like this part and this inferior frontal part. And logic network usually looks like this. Just look at the green blobs. So in my study, I'm going to investigate the neural basis of programming and compare it to these hypotheses. So in my first experiment, I'm investigating the brains of Python experts with at least 5 years of programming experience. When you see this, you know what will come next, but yeah, don't spoil it. So these are PhD and postdocs in computation-intensive fields of study, and I evaluated their programming skill using a programming Python test to make sure that they really know what they're doing. Okay, so I mean they know how to use Python very well. Yes. Okay, and I use functional MRI as my neural imaging method, and the data analysis includes univariate contrast between programming task and a control task to isolate the cognitive activity specific to program. And then there is multivariate pattern analysis to uncover the neural representation for algorithms that include the support vector machine classifier to decode different categories of code, and the representational similarity analysis to look at the more fine-grained structure of the semantic contents of the code. So in the task, participants solve simple Python functions like this that's doing some nonsensical things to any input character string. The participant just took like 24 seconds to understand what it would do to any generic input. And then they saw a specific input and took a few more seconds to derive the result. And lastly, they saw a proposed result and answered whether it was correct or not. So in this 3-step task, I only analyzed the data from the first step, where participants are building a general understanding of the algorithm without any confound coming from the using the algorithm to actually do any computation for any character string. The control task for this experiment is to memorize the scrambled lines in a scrambled function. And then they memorize an additional scrambled line. Lastly, they saw a single line and answer whether they had seen this particular line in this current trial or not. And I localized the language network using the sentence reading task. People judge whether the two, this active voice and passive voice sentences, whether they have the same meaning. And for the logic task, they judge whether two logical statements are valid inferences from each other or not. So here we have the language brain, we have the logic brain, and we have this thing coming from the contrast between reading Python functions and memorizing scrambled random stuff. So all these maps are kind of conceptually overlap across participants. So the first observation here is that there is some consistent activation across participants. Otherwise, nothing will show up on this average map. So we can kind of rule out the first possibility that everyone learns through a general purpose learning mechanism and come up with idiosyncratic neural basis for programming. So next, let me highlight the overlap between logic and code and language and code for you using blue color. And then I quantify this obvious difference in overlap using the cosine similarity matrix between these activation maps. I did this overlap measurement within each participant and show you the average over here. So we see that the programming code is activating the reasoning network. But does this already show that reasoning is recycled for programming? I would say not yet. We need one more piece of evidence. Just think about this. If I can distinguish dogs from cats, but I cannot identify any specific dog breed, can I call myself a dog expert? I don't think so. No. But I can tell some dog breeds. Yeah. I think I like Airedale Terrier. That's my favorite dog. Okay, anyway, so the same goes with the reasoning network. If all it does is to distinguish code versus non-code, I wouldn't say that it's caring that much about programming. So it has to differentiate between different algorithms described by the code, because the algorithm is the essence of the code. Well, at least it should distinguish between the two most common control structures, the for loop and the if conditional. And when I designed my study, I had this consideration in mind. So half of my stimuli contained a for loop, the other half contained an if conditional. And I tried to do the decoding using the neural activation patterns. So what happens here is that in each region that we care about, there is a neural activation pattern for each function they saw, and I just took these patterns to train and test the support vector machine classifier to differentiate loop from conditional. And I'm going to show you the decoding accuracy in two crucial regions in the reasoning network. That's the IPS, that's the intraparietal sulcus, and the PFC, that's the prefrontal cortex. We also have this A1, which is primary auditory cortex. It serves as a control because in this task, this task is purely visual and not audio. So this auditory cortex should not care about the algorithms at all. And that's what I found. In reasoning network, the decoding accuracy is significantly above the chance level of 50%, while in the A1, it's like a chance level that's no better than random guessing. So programming code activates the reasoning network, and the reasoning network contains the neural population code to represent the underlying algorithms. So this is kind of evidence that the reasoning network is recycled for programming. But at the same time, the language network is not doing nothing. When I try the same loop versus conditional decoding in the language network, particularly in this lateral temporal cortex, I saw a decoding accuracy comparable to the reasoning network. And I did the control analysis to make sure that this decoding is really about the algorithm and not just the presence of keywords like for versus if. So that's kind of weird because the language network is not showing too much of a response to programming code. That's kind of weird. So to confirm, I just looked at the activation time course of in these networks. So just look at the solid line. This yellow-orange line is the activation, the neural response to programming functions in the reasoning network throughout an average trial. And the language network, that's the blue line. The dotted lines are the responses to the scrambled memory control. So as you can see here, that response in the language network is really weak. But weak as it still has a peak. And this tiny peak in the language network happens much earlier than the large peak in the reasoning network. So since the language network is doing some weak but fast response to programming code and still encodes its algorithm. So based on this finding, I propose this model of code comprehension. When we read a piece of code, information comes in from the visual cortex, it gets processed by the visual word form area, and then the language network do something like a triage. It creates some kind of surface level representation to have an initial taste of what the stimuli is like. And when the stimuli are not typical sentences, this surface level representation is not processed further. Instead, it's related to the reasoning network to create some kind of functional entity complete with executable algorithms and all the variables within it. Of course, this is very hand-wavy, it's hypothetical. Then it's one of my future directions to verify this model by using some more highly temporally resolved data with the interaction between these different networks. For the first question here, I'll say the answer now is that programming primarily recycles the reasoning network with some support coming from the language network. But this activation profile is observed in programming experts who have dabbled in this arcane art for several years. So the next question is, what's the trajectory of this learning? When does the expert-like neural profile emerge? It's possible that maybe the reasoning network is really almost ready for programming. It only takes some initiation to recycle it for this task. Or perhaps it could be that the reasoning network is not really that good for programming and it takes years of experience to build the infrastructure for it to really do the programming stuff. So to find out this, I have to study people with limited programming experience. And that would be the programming novices. Yes, all this coming. Programming novices, which I recruited from a introductory programming course. They have zero experience prior to taking this course. So before the semester, while they were still novices, total novices, I scanned them once, but that's for later. I will talk about later, just wait for it. And after the semester, 1 semester of training, and they became programming beginners. I scan them again. This time they know how to read code. I can show them the Python function reading task I show to the experts. And the result shows that even after just 1 semester of programming course, these beginners are using the reasoning network to understand Python functions. And then their reasoning network can differentiate between loop and conditionals. And based on these findings over here, I would say the recycling of the reasoning network happens quite rapidly. Only 1 semester is sufficient to recycle it. Okay, so now we show that in the brains which already know how to program, the reasoning network responds to Python functions, and then it represents the underlying algorithms. And is this ability recycled from some pre-existing function of the reasoning network? Yeah, that sounds kind of vague. To rephrase this question, I would say, does the reasoning network already respond to algorithms before we learn how to program? Before learning programming, the ideas of programming languages are new to these novices, but the idea of algorithm is not. We encounter algorithms every day in the form of recipes and Lego building manuals. And so in the brains of these novices, is the reasoning network in charge of understanding these algorithms? Or perhaps in the brain of these novices, there is another system that's doing the comprehension of algorithms. Maybe let's pull out the language network again. Perhaps that's the guy. So instead of these recipes of Lego building manuals, I'm specifically interested in the programming algorithms, the same algorithm that I show these students as Python functions as after they learn how to program. But as for these novices, obviously there is a technological hurdle here. How do we present these programming algorithms to students who haven't learned how to program? The solution I came up with is something I call pseudocode. I add quotation marks here because I know it's not the kind of pseudocode software engineers talk about and use as drafts of the program. Here, my pseudocode means a plain English description of the Python functions I use in the other part of my study. So the example would be like, input is a word, result is a list containing another word. For each character in input, repeat the character 3 times to make a new word, and then update the result list by adding the new words to that list. Okay, the control task for this one is to memorize sentences in a nonsensical passage. So each sentence in this nonsensical passage, they are grammatically legit, and they're made from words taken from a pseudocode passage. But these sentences as a whole, they don't constitute any executable algorithm. The reason for this, instead of randomly scrambling the pseudocode, is that I want to subtract away the effect of sentence reading through this contrast. Because there are sentences in the pseudocode, so the language network will obviously get involved to parse these sentences. So I want to know whether there is anything in addition to sentence parsing that's underlying the comprehension of algorithms. And the results show that there is, yes. So in novices, before they learn how to program, pseudocode already engages the reasoning network, just like Python code engages these same participants after they learn how to program. And again, in the brain of these novices, we can decode loop versus conditional algorithms in the plain English pseudocode. Okay, so far, I have done a lot of things with these loop versus conditional decoding. The next, I want to do more with these novices, which is I want to understand the more intricate structure of the semantic representations of these stimuli. So for these novices, they saw dozens of code or pseudocode within each scanning session. And then they saw the same algorithm written as pseudocode before they learned how to program and as Python functions after they learned how to program. And then each of these algorithms differ from each other along some semantic feature dimensions. Some of these features are hand-coded by myself when I created this stimuli to differentiate the stimuli from themselves. So these features include the loop versus conditional control structure, or maybe the difference in the data type of the result. And the target of the control in the for loop, that would be the thing that the loop is looping over. and then the operation taken into control, like a repetition, like appending something to it, like reversing a string or whatever. The semantics of these algorithms can also be measured post hoc as the vector embeddings of these stimuli in large language models. For pseudocode, I'm using this specific model from OpenAI. That's the latest one available to me back then. And then for Python functions, I'm using this CodeBird, which was trained specifically on programming scripts, documentations, and comments. Okay, so these are ways to quantify the semantics of the code. And the analysis I'm going to tell you next is based on the idea that if two algorithms are doing similar things, the neural representations should also be similar. This kind of similarity can be captured in representational similarity analysis. It's a tongue twister. Okay, and yes, the idea is that there are, for each participant, they saw n different stimuli, and then in each tiny patch in their brain, there are n different spatial activation patterns for these n stimuli. And just take each pair of these activation patterns and compute their correlation to derive an n by n neural similarity matrix. As for the stimuli, I also computed an n by n feature similarity matrix based on some features of these algorithms themselves. Then I just took the correlation between them to derive the value for that one patch of the brain, and I just did this for everywhere in the brain. So in this analysis, I compared the neural pattern similarity to two features. The first of all is the meat of this analysis, which is the meaning or semantics of these algorithms. It's a weighted sum of the similarity matrices derived from those hand-coded systematic features and also their vector embeddings in large language models. The second one serves as a control. It cares about what the stimuli kind of look like to the participants. So specifically, it measures the length of the stimuli in terms of their characters or word count or token count. So these are the two things I'm comparing to. Let's show the result. First, just a reminder, we have novices. That's before they learn how to program and they read plain English pseudocode. And we have the same participants after they learn how to program and they read Python functions. For the appearance features, nothing is on the outside surface of the brain. The only blobs I saw are on the midline surface of the brain, close to the back. That's the primary visual cortex. So that's good. The appearance of the stimuli are reflected in a part of the brain that cares just about the appearance of things. So it means our analysis is working. As for the meanings feature, it is represented widely across the brain. We have in the reasoning network. We also have extending into some of the language network. And in a separate analysis, I did a direct comparison between the neural similarity structure of pseudocode versus code before and after they learn how to program. And I found significant similarity between those representations. So it means that through a programming education, the neural population code to represent plain English algorithms are recycled to represent Python functions. Okay, so the answer for this one is yes, the reasoning network is recycled for programming because it has this pre-existing ability to understand algorithms. So based on these findings, we should predict that the reasoning ability is a predictor of programming learning outcome. Is that really the case? So of course, there have been behavioral studies showing the correlation between reasoning ability and programming learning outcome. But my study is adding to the literature by including reasoning tests and language tests in one analysis to show that reasoning is more important than language. So among the many reasoning tasks I gave participants, some examples include this Raven's Advanced Progressive Matrices test. That's for abstract fluid reasoning. I also have things like a number approximation task. It's a validated psychometric test for our number sense, which is also an ability attributed to the reasoning network in neuroimaging literature. For the language task, we have something like a sentence comprehension test. It contains sentences with different degrees of grammatical complexity. So some sentences have like syntactic movement. It means that the object and the verb is distinguished, is separated by several different words to make the sentence more difficult to understand. And we also have garden path sentences. And for this language task, there is also this Peabody picture vocabulary test to evaluate the vocabulary size of the participants. As for the outcome measures, I operationalize it as the course grade of the introductory course and the participant score on the Python problem solving test that I developed specifically for this task. And I also include this Python syntax knowledge test as a kind of control. This one is more like a rote memory test, so I don't expect it to be predicted by anything. Okay, more specifics about the outcome variables. First of all, we have the course grade is trivial, just ask the students for them. And what else? And then we have this Python problem solving test. So in an example question like this, there is a function with a blank. And then there is a specification for what this function should do when the blank is filled, and the participant just answer the question accordingly. As for the Python syntax test, it's just multiple choice questions for textbook Python usages, like how to put parentheses, how to create a dictionary, that kind of stuff. And again, this one is a control. It shouldn't be predicted by anything. So before I show the results, let me appreciate my data collection squad. Without their help, I couldn't have conducted like 7 behavioral sessions for each of the 50 participants. And among those 50, 22 of them had additional 2 MI scans, one before, one after the semester. So that was a lot. I couldn't have done it by myself. So the results. The Python problem solving test score is predicted by their reasoning abilities, but not their language abilities. That's also true for the course grade. As for the syntax test, syntax knowledge is not predicted by either. An interesting observation here is that in the Python problem solving test, there is this lengthy specification of the function, and it's written in plain English, and the participant definitely have to read the stuff to understand what's going on. Even if that's the case, the test score is still predicted by reasoning ability more than language. Okay, so my answer for this one is yes, reasoning ability is predicting programming learning outcome. So these are the things I have answered so far. So we all have this pre-existing ability to understand algorithms, and learning to program recycle that ability to understand programming code. And then the reasoning network responds to Python functions, and then it represents the underlying algorithms. So these are what I've got for the answer for the first question. How does our brain enable programming? For the second one, it's about the future directions. We're finally reaching this place. Good. So the ongoing project right now is that I am collecting data from a new cohort of experts and novice/beginners. Using exactly the same task, exactly the same stimuli. Because previously, when we conducted this new experiment with these guys, we used a slightly different stimuli, but the same design philosophy, but slightly altered. So now we're doing the same task, same stimuli to try to find out whether there is what kind of neuroplastic changes take place as one gain programming experience. I want to find out the quantitative difference in how their brains respond to Python code and how distinctively their neural representation is for the algorithms. Another ongoing attempt is something like event segmentation. So when we read a piece of code, we go from knowing nothing at all to finally understanding what's going on. So it would be great if we can capture the transition of these states, or maybe the moment of like epiphany to finally know what's going on. A technical challenge I'm facing right now is that so far I have been letting my participants read the code or pseudocode for the whole duration of 20-something seconds without any monitoring, so that I don't know when they are looking at where I'm in the code. I can of course still do some unsupervised segmentation using things like hidden Markov model, but the tricky thing is that I don't have a ground truth to compare with. So a reasonable next step is to combine behavioral tracking like eye tracking or maybe keyboard tracking if you want to study code writing, so that we have temporal information for what they are doing at each moment. And then we can ask questions like, how does the neural representation of algorithms evolve, perhaps throughout one programming session, or even longitudinally along with the accumulation of programming expertise? So one question relevant to this event segmentation is chunking. So when we read a piece of code, we don't usually remember every implementational details in it. At some point, we will abstract it away as a black box and just remember the most important thing, that it takes some data to churn out some figure. So what happens in the neural representation when it changes from containing all the detail to just having the most highest level abstraction? And what happens when we have to unpack the chunk to retrieve the information? So this question is not only interesting to cognitive neuroscience, it may also have some implication for AI design, I suppose, because right now AI models are constrained by limited context window and memory. And there are some attention features to try to prioritize some information within the context window to have the model do more things under the constraint. But another interesting direction would be to let the model actively and dynamically chunk away unnecessary informations and learn when to unpack the chunk to retrieve the information when they become relevant again. Okay, so these will be possible when we combine neural imaging method with behavioral measurement to do multimodal measurements. In this case, the neural imaging measurement doesn't even have to be functional MRI. It could be functional near-infrared spectroscopy. That's another tongue twister. Also, electrophysiological measurements like EEG. So with these kind of more portable devices, there will be more naturalistic experiment designs. We can just have a programmer sit in front of the computer, do their things, and kind of have them hooked up to all these measuring devices. The neural imaging, eye tracking, keyboard tracking, and even a microphone to record what they murmur to themselves while they are thinking aloud their solutions to a problem. This kind of naturalistic paradigm will allow a more sophisticated comparison between experts and novice/beginners. So it's possible that their difference lies not only in how their brains represent algorithms as a spatial distribution, but also in how temporally these representations evolve. Or maybe we can say the difference lies in the high-dimensional spatial temporal manifold. Yeah, that sounds super majestic when we say manifold. The sense that's just good. Yes. Okay, another group of people I would like to compare with is the vibe coders. So people who code solely through the interaction with AI chatbots. So when they solve programming problems, is there any, there must be some behavioral pattern or neural signature that differentiate them from people who receive structured training like software engineers. So these questions will have educational implications, and I seek to explore them in my next grant. So all the works I have shown you so far, they have been supported by an NSF grant, and I plan to apply for a new one. Yeah, actually, before I got the invitation letter, I was just discussing with my supervisor saying, hey, we should get a new grant or something. Yeah, that's the thing we're working on. The new grant would be on the science of learning and augmented intelligence. Yes, that's the title. And the comparison between the experts and novices, as well as people with different levels of interaction with AI, that would be a central theme of that new grant. And speaking of education, another question I'm thinking about is like sensitive or critical period. So is there a best time in childhood that's the most optimized for learning programming? Perhaps like kids will have some time in their life that maybe they even use a completely different neural mechanism to learn to program as me, who learned programming in late adolescence or even in adulthood. Yeah, I'm still not in my late adulthood. I'm probably in my adulthood. Yeah, 34. Yes. Okay. So this might have implications in so eventually it would be great if we can apply this research to K-12 education to have some education devices created for the teachers and students to use. Okay, and along the way, when we learn more about how our brain learn programming, we can help people learn programming better and make programming easier to learn. And along the way, one natural byproduct would be having a very naturalistic and multimodal, rich data set of human computational thinking. So that would be something like this fMRI data set of natural story listening that I helped put together when I was in Princeton working as a research assistant. And also, this research program as a whole contains a lot of components from neuroimaging to behavioral tracking. And I can imagine that would be a lot of hands-on experience for my trainees. Yeah, and of course, I will also learn a lot together with them. And the one thing I can think of right now is that since many of these projects requires programmers from different degrees, different levels of expertise, and the students will definitely use programming to analyze data. What about I just have the students maybe scan themselves and learn to analyze their own data? I don't know. That's one idea I have, a vague idea I'm having right now. There will definitely be more way to engage my trainees than I can think of right now. Okay, so I think, yeah, here, Alaska Institute, a lot of water is the best place for me to pursue this research program. Not just the programming project that I have been dreaming about, but also my broad interest in how human brains interact with technology. And here we have so many experts in different fields of technology that I can collaborate with and ask some maybe naive questions right now because I just think of them on top of my head. Some questions like, how do our brains adapt to previously never thought of ways of human-machine interaction, right? What differentiates between the virtuoso and a amateur musician in terms of the brain dynamics? But I guess this problem is kind of answered a lot, but there is maybe more to study. And one thing I'm thinking about is that is there any similarity between composing music and programming? They're all structures, but that's some question we can ask. And also some more questions I can ask is like, how do our brain navigate a programming world with augmented reality items floating around? How do our brain differentiate between actual and virtual items? And also, I'm interested in how do we incorporate how to incorporate novel fabrication tools into our mental imagery of the products or outfits we're designing. And these questions sounds kind of exciting to me. I don't know what about you, but just thinking about these questions is already mind-blowing to me, and I can't wait to start the exploration. So basically, this concludes my a brief introduction to my work and a rough sketch of my future directions. And comments and questions are all welcome. Thank you so much.
Okay,
All right.
you want to stand? You want to sit down?
Yeah.
Will your computer in front of you?
Maybe I just get it.
Just stand.
Yeah.
Just have your hands. All right.
Okay.
Question. So, I'm interested in one of your discoveries that language ability does not predict how well you learn programming as well as reasoning abilities. But because for me, I would not think that language abilities means how well I speak English right now. They're rather like how quickly I learn a new language, for example. So, how do you think that maybe there's difference between these two kinds of experimental setup?
Yes, okay. You asked.
Could you repeat that for this?
Oh, okay, yeah. So just there are different components of language, and maybe language is not just about how good I speak English, but also how fast I learn a language. And does this kind of predict programming learning outcome in some sense? Okay, and that's good because there is another behavioral study that shows that language aptitude, that is the thing you're saying, how good people learn a new artificial language, that kind of predicts how fast the people go through the course material of an online programming course of Coursera, Code Academy. Yeah, so language ability is related to the learning speed, yes, of programming, but maybe not the eventual achievement of this ability. yeah, so it's related to how fast people would learn. But of course, there is we can always try to replicate this finding to see if that's true, but I think that sounds pretty plausible.
Yeah, that's a great question.
No problem.
Yeah, no, this is fascinating. And I mean, for me, I tend to think from like an engineering point of view, and whereas this is like a scientific point of view where like, you discover the new thing.
Yeah.
If you, for example, have any implication for like an engineer like us, like for example, this kind of stuff can be used for like a new type of programming tool or learning, you know, curriculum or whatever.
Mhm.
How do you, what kind of implication can you suggest for to use that kind of apply this kind of knowledge?
It's kind of knowledge, getting for the reasoning, the importance of computational thinking in this in programming. So right now there are already some groups, I think in MIT, that's creating this programming language for children, which is called Scratch Junior. Have you you know, yeah. So I think that's kind of an implication here that they get rid of the language part, get rid of the things that looks like sentences, get rid of the involvement of words or something, and they just focus on the algorithm, like how to make the cat move. So this is kind of like a support for their attempt to teach children to think through the things rather than starting from, okay, this is a for loop, this is if conditional, you have to learn the syntax rather than this. But another thing we can think of right now is that if we can do something like e.g. Measurement of programmers' response during programming, maybe we can do something like neural feedback, like when we can identify when they get stuck in their thinking process. And maybe we can just combine it with this AI thing. It knows the pattern of stuck, and then it will suggest some hint that may help you think through the problem.
So Mike, I have a question of my own, but I will do Mike reverse question first. Is that I believe you mentioned a study with bilingual users. Were there any differences, for example, in brain activation between users who learn English as first language versus English as a second language? And he apologized that he come from a meeting, so he may have missed it. If
Oh, yeah,
talk
no
about-
problem. So in this behavioral task, I'm having this part as my one of my language ability measurements, which is the age of English acquisition. So obviously my participants are from all kinds of backgrounds. And yeah, in Hopkins, I would say there are a lot of
So you did not find any differences? Depends on when they get English
Yeah, no.
acquisition?
Yeah, no.
So I have a question on my own. So anytime who asks me to count, I will go back to Chinese.
Oh, yes.
And I
I
want
think
to do it in English.
Yeah.
So now I'm curious, when I count in Chinese and when I count in English, do they activate in the same place?
Counting Chinese and English, I think there have been study of math, symbolic math, and I think as long as people are counting, like you alter a kind of thing, you say something that's a part of a language, but the things you are counting is in charge of the same, is handled by the same region in the brain, the number sense region. So maybe that's because like the mapping between that abstract number idea to the language you are most familiar with, maybe that's a part of the language networks working, not the number networks working. So yeah, but I also understand, yeah, whenever I count things, whenever people ask, what's your phone number? Cheating or is she? I don't know. Yeah, seven, all, two. Yeah, I just lost track of that. Yeah. Hi. Yeah.
No.
Thank you for the amazing talk. One question about the relation between human and like programming and in the future, like in 5 years, like what do you think? Like for me, like programming is just for a tool to make something else
That happened, yes.
like app or like anyway. But what do you think about the program itself? Like do we need that tool in the future?
I think in the future, maybe we don't need that many different kinds of programming languages. Maybe they will come across, but yeah, I think when people develop all kinds of new programming languages, they always thought this is the universal programming languages. You don't need other programming languages for this. But I just think just like now we have this AI thing, it's more like translating between different programming languages. So it doesn't invalidate the existence of each language, but it's just that learning the specific syntax of the language is not really that important. And maybe the more important skill right now is to write out a good pseudocode to communicate with others. Like if you sometimes like people, when we do some, how to say that, revamping some legacy lab scripts written in bash script. And I just feel it's super horrible. But if the people that originally wrote that script just write out their logic as a pseudocode to me, I was like, oh, I know what's going on, but why do you use the if and fi? What? That doesn't make sense. I mean, it's creative, but it's just hard to understand. So maybe in the future, programming languages can still exist. It's just that people can communicate across different programming languages more easily.
Yeah, we don't actually need to write program anymore.
Yeah.
Actually, so
Yes.
from natural language, we got to
Yeah, not really worse.
But still, I think the mindset might be.
Yes, mindset is
You
important.
you mentioned like vibe coding stuff, so that might be
Yes.
interesting.
And also things like we still have to understand the programming language enough to validate the output to know that's doing the thing. So yeah, I think it's still important to learn a little bit programming languages such that you can understand what's going on.
I have a similar question. Thank you for your talk, by the way. That was amazing. I wanted to know that if you had the opportunity for the CEOs of Anthropic and OpenAI to be in this room, what would be the number one most important question that they would ask you as an expert in your domain, and what would your answer to it be?
Well, I have to imagine their questions.
Yeah, you have to imagine what their question is for you.
Oh, okay. So I have to, yeah, like mental tracing, really, mental profiling. So I guess they will care the most about what does this say? What is the implicational value of all these things? And yeah, what I can think of right now is again the e.g. behavioral pattern tracking thing, such that we can everyone like has been talking about this since like 2010 or even before that, like mind reading thing. Can I just think what I want to type and to have it typed out? And people have tried to do this with language, but language is very dynamic, very complex. But perhaps for programming, it could be a little bit easier because it's more constrained. Maybe there is easier to find out the neural signature for a particular structure of programming, like we are doing a loop here, like we are doing declaring the function here. Maybe we can capture it using these measurement and then wire it up to the AI to have it not on to have it like bypass the stage of typing out the comments. Because whenever I type out the comment, I still think, yeah, my poor English. So do I have to ask the AI to polish my comments first before I show the comment to the coding copilots? Yeah, so if we can bypass that stage to just think what we want to do and have things done, that'd be good. And I guess that's the thing these AI companies might care about. Another thing they would care about is to secure their RAM. Yeah, which is but yeah, I cannot help with that. Yeah.
Actually, kind of came up with a question from that perspective. I didn't ask, but one of the questions they might be interested in, and I'm also interested in, how can this kind of implication be used to understand how LLM thinks? For example, one of the interesting finding in AI community is like a chain of thought. So he just kind of, he just specified that thing, that step things step by step,
Mhm.
and then their answer is much better.
Mhm.
Right? Just only adding one sentence for the prompt. But actually, we don't know why it works in
Yeah.
that way. Right? So I guess some of the neuroscientific perspective might help AI researcher understand better about LLM, how LLM thinks.
Yeah.
So I don't know how actually you could apply for it, but that kind of the understanding not only for human brain, but understanding LLM might be kind of
Yes.
quite interesting research domain.
Mhm.
Might maybe like Anthropic label there, I feel interesting.
Yeah, that's right. So I think in the AI plus cognitive science domain, they have been using a lot of this representational similarity analysis. They just pull out a particular part of the brain, pull out the response from a particular part of the brain, and pull out the response from a particular layer of the AI model, which should represent the same things, and they do these similarity matrices to do comparison between them. But that's usually done in like more like a visual recognition, like more the vision model, not the high level thinking, like programming stuff. But if we can compare this representational similarity, one thing they are trying to do now is to train a process reward model, which encourage the model to generate the similar internal representation of things as human beings, rather than just replicating the outcome, which is called outcome reward model. Yeah, they're trying to do this so that the machine can know how to think rather than just what to behave, what to output. Yeah.
There was a request to repeat the question.
Oh, repeat the question, previous question,
Make it just one sentence.
one sentence.
Which
Yours question.
LLMs.
LLMs,
Yeah.
yeah, the application of this
Yeah,
thing to
application.
LLM. Then how can this neuroscience thing help us understand what's going on in the LLMs?
Right, and then I'm not any of the CEO, CTO, but I would be curious to know what kind of tasks I can do with people before I hire them? Or from your study, how do we figure out different strategies to teach programming? Maybe
Mhm.
certain people,
Yeah,
how do we train them for logical thinking? And maybe they have very good language ability,
yeah,
and maybe, and you talk about vibe coding as well. So is there differences between how they respond to?
yeah, how to respond to programming problems, yes.
Yeah, I think those are interesting. I want to know more because then maybe I know how to, it kind of, you want to speak the right language with them so they got it. And I think we talk about metaphor, I don't think, and sometimes some people don't get it until you start using metaphor.
Yeah.
But it's still reason.